Hello, my name is Dmytro. I'll be presenting on the project I worked on as part of the Air Lab. So right now, the work is still ongoing, and I'll be talking mostly about early experiments, potential future setups, and just overall direction and the thinking process we're going through. So the overall structure would be that I'll be talking a bit about the inspiration, some constraints that we were taking, and some design principles that we're taking from previous projects. A bit on the prior work that is the most, I would say, similar to ours. And then just going through architecture and different design setups we came up with, and later our general setup and the plans on experiments. Okay, so on this slide we're going to focus a bit on the inspirations that we took from previous projects and also some of the limitations we're thinking of. It's not specifically prior work, but there are a couple of things that we consider from here as part of our design principles. So for instance, UPenn group had an interesting setup with a UAV-UGV collaboration where UAV would provide top-down view of the site basically, and UGV would try to use an LLM both with tasks on both completely self-deployed on-board LLM, something was done for the first time as the claim, and something we also wanted to use. And also the test that with API typical based requests, something we want to avoid as well as they did basically in a sense, because connectivity is not something that is constantly available if you're thinking about outside navigation. But in a sense, because of the UAV, they had this sort of hard priors in a way that at first would be the UAV mapping everything for them. And they were also having a bit more of the complex instructions, and that's something we want to avoid to possibly reduce the rate of hallucinations. But I'll be talking more about the project slightly later, but let's still focus on this. So we also thought of potentially, they had both the distilled model and non-distilled model. We thought of potentially avoiding fine-tuning because it would be interesting if we could have a self-deployed local small language model, and basically going for a setup that doesn't require further fine-tuning if it could perform well enough. It's also important to mention the work done by Samex, the original object navigation project. But then the thing is with how they approached it, at the time it was great, but the thing is if you think about the outdoor navigation, the problem is the environments are not as structured. And that's something to be mentioned in the Dragon paper, how to not train your Dragon. It's a bit of a problem to be thinking of outdoor navigation, for instance, if we're talking about structuring the environment, because not everything can be easily hierarchically structured. We cannot instantly assume that, for instance, in the Samex paper, you could assume that you could have some sort of priors and understanding that, okay, in the kitchen, you typically can find the fridge, right? It's not the same with outdoors. Sure, you can sometimes assume that in a parking lot, you can find the car, but it's a bit more loosely structured, right? If we're thinking about where do we find exactly the field or some sort of building if we're in a rural area, right? Maybe next to a road, but doesn't happen constantly. So structuring some sort of scene graphs, it's a bit of a problem for outdoor navigation. And even so, it's been done partially before. And also having some sort of priors would be a bit more difficult in outdoor. So that's what we can take from here, partially, in terms of understanding how we can design external projects about thinking about outdoor navigation, but I'll talk again about our project in specific slightly later. Now, let's talk about actually the most relevant to us work, in the sense that this is the outdoor navigation where researchers focused on specifically on looking for the hidden targets or object search where you actually care about including reasoning and actual thinking for the multi-step decision making as you're looking for hidden targets and not just a single object navigation with exploration and mapping. Because here there's no proper mapping happening technically with the reasoner explorer, the word that's most similar to us and how it tries to approach the problem of finding hidden targets. The idea is that they would plan out different possible paths, and they would have visual descriptions provided for each path as possible as given images on how possibly relevant that path is. They would use also an LLM API call. They would try to score the relevancy of it, of the descriptions, visual descriptions to the final target, so as to understand to which path to go to with the highest score. So it's really interesting because, again, no hard priors, they basically deploy themselves. But a bit of a problem there is some of expectation that the call is eventually could be found in a bit more of like direct, straight direction, and definitely smaller environments. And then if we talk about multiple requests, then if we'll be thinking of actually deploying a local LLM, but then multiple requests, multi-inferencing on single edge device is not something that's feasible. And then the metric that they provided, the new one for this like scoring, was the thinking time and traversal time, is a bit difficult to interpret. And baselines, because the project was a bit older, which is fine. Their first version was released in 2023, when only the first like open source models were coming in, and it was still the mostly reliance on older API-based models. But then they also mentioned doing a human-like search only in the conclusion, which is okay, but we believe that this direction of thinking of the human-like search is a bit more interesting and could be explored a bit more. So we'll talk about that later in our projects in specifics. Let's touch upon the language of guided object search in agricultural environments. So the idea there was that they would have a UGV, robot spot, going through a loosely structured environment where they would first like try to memorize the locations on different objects. So they would use a YOLO model for that, if I'm not mistaken. And the idea was that they would try to do logic extraction, so trying to score a bit more on the reasoning of the LLMs. So they would ask like, where possibly could the target object be located? And they used loosely structured environment because they were looking for objects, for instance, placed on tables. And it has a bit, it's loosely structured because like you can assume, despite like farms being a bit more chaotic, it's still possible to assume that while some sort of screwdriver can be on a table next to some other object, like there's also used for repairing something, right? So they would do object-to-object relationship scoring, and in that way they would try to figure out next to what object is there most likely to be the target object, and they would look into previous coordinates of that object was stored. So this is an interesting approach, like something that they need to think about when trying to think about how to possibly score and be a bit less reliant on some sort of LLM outputs and possibility of hallucination. But again, not specifically like what we want to work on as they do pre-memorization. And there's also proximity assumption in the sense that like loosely structured like farm environments like in the UGV, it's not something you want to work on. The next slide, I'll finally explain what's the target. Let's finally talk about our research goal. As it was hinted before, we would be likely slightly working on something onboard and without hard priors, related to outdoors definitely, and something related to object navigation probably. But let's talk about first about the different levels of difficulty that the Reasoner Explorer defines specifically for object navigation. For instance, level 2 would be defined as object navigation based on the conditioned on some other object, like for instance, avoiding forest. Level 3 would be conditioned on path, like choosing and following certain path before finding an object navigation goal. And then for level 4, it's something a bit more abstract, definitely requiring ambiguous like instruction understanding, so possibly some sort of reasoning model. But then the thing is, I believe that these level definitions are not capturing full of the object search spectrum, because if we just, without going too much into depths of possibly trying to predict like how humans think on the cognitive level, right? But some sort of like human search or like object search resembling how humans do it, we can think that people typically have some sort of like prior associations as where to find the possible target. Like for instance, if we're thinking of a car, well, in some semi-urban area, you could be thinking of a parking sign. Then, well, if there's a parking sign, there could be a parking lot, and eventually there will be potentially a car there, right? And then humans would also explore these different like sequences or chains of clues, right, before finding a final target. But then there is a possibility of dead end, right? That a certain promising direction doesn't pan out and just doesn't work for you, right? So most of the object navigation projects that we look for right now, they have sometimes the attempt at recognizing whether they achieve their task by querying again the VLM or having some sort of object detection confirming that they found their target. But then it's usually used mostly for metrics. It's not used for understanding that, okay, like if we fail, there must happen some sort of re-evaluation, right? So when a human searches for something, if they fail, they try to think of like, okay, what were the other like promising directions I could go for? Like if I'm stuck here and I've reached a dead end. So this is something that object navigation and outdoor settings like projects do not do. And this is something I wanted to tackle on specifically in this project. So let's look at the specific scenario on the left. So this was taken from Google Earth. So imagine if we start in the this starting area near the number 1. When our drone starts and its final target is given as basically a boat, it has to find a boat. It would potentially initially see that there is like a small patch of water and would try to reason that, okay, well, there is a patch of water, there's probably like a boat there. But then when it reaches it, in the middle of navigating towards the second stop, it would potentially see the next patch of water. And this is how like, a human would probably think. Like they would just remember there was another patch of water as a promising direction. This is something that most of the object navigation projects don't do. They do not try to memorize possible alternative directions and backtrack properly. So our drone, let's say a drone or the object navigation system's reasoning, would go towards the second step, and then I would see that it's just a lake without any sort of boats here. And this is how what we want to work on and work on specifically in this project is trying to distinguish ourselves out of other like object navigation methods and focus on this problem of trying to remember previous and having like ability to query previous experiences to understand that, well, there was another patch of water, right? So if we were to actually like assume that our reasoning navigation system includes memory, it would be able to understand that there was another like possible direction to go to. So we would then move to step 3 and finally find our boat here, right, on the Nile Lake. So that's what we want to have. We want to have end-to-end in the sense that we wouldn't just stop at the first failure. We would continue searching by querying our memory. So end-to-end object search system for UVs and ability to have this like multi-step setup, dead-end recognition, and memory-based alternative formatting. That is slightly or loosely be inspired by human search behavior. No hard priors, so no satellite images, pre-existing maps, and we, as with the UPenn group, we specifically, as they did it, as some other projects are doing it, there's hope to be relying less on the VLIs and specifically discrete actions like going up, left, down, right. With the drone, more on the decision making on possible direction to go towards to, but then hope that we can just give a task to a low-level planner that would classically navigate towards an object or else. Right, and then single phase in a sense that would be a cold start to where we don't have to do some sort of, again, like pre-mapping, pre-memorizing. And this is the hope to how we want to distinguish ourselves a bit more from previous projects that used, like, for instance, some sort of regs, scene graphs, etc., where sometimes they would have to first like go through an entire area and then query their database to find possibly some targets, right? And then large scale for the reason because, like, as seen in this scenario of navigating and finding promising directions and thinking about it, this is actually that typically requires like larger environments, and it's a step towards like properly using memory in these environments. And outdoors is overall like less explored, with a ratio of outdoors projects being way less than that of those covering indoors. So this is our general focus. Yes. Definitely something that gets swapped, but the main goal of introducing memory for object scale outdoor object search still remains our main goal. So we initially thought of using some sort of object detection plus LLM reasoning about the sequences of objects and trying to find these like hidden targets in outdoor environments. But then we thought that even it would be definitely more useful to have more descriptions about the environment to probably reason about possible hidden targets. So we decided the VLM is basically a must here to have proper scene captioning. And plus, currently smaller open source VLMs, their like architecture is fully accessible. So we thought of what we do basically is we access this two-tower architecture with the visual detection encoder, and we specifically separately query the LM part for it so as to save some space. And because the idea is to have it on board, so we're using a smaller VLMs that is quantized. We're using the same like language part to query it separately without images to create some soft priors. So the idea is we're initially given a final target. Let's say we're searching for some sort of basketball court, and then we can understand, we can have some early associations that our language model can provide, that basically basketball court, that can serve right as a context later that can be helpful for us. This association could be that basketball court could be found near typically some sort of recreational area, sports area, or parking lot, or some sort of like gym center or else, right? So the idea is we would be getting the soft priors, we would be getting the scene caption, and then we would basically query our VLM as to where to go to that is most relevant to our final target, for now at least, unless it's visible, of course. So our output could be move towards far left red bush. Then to rely less a bit on this sort of directional suggested output from VLM, we would have an object detection open vocabulary YOLO-E module that is prompt driven. So it would accept a prompt like far left bush, red bush. It would, as you can see, would be able to identify it as it did here. And then we would also have a bit more of the partitioning to later confirm it with the VLM. So we would have this partition named as leftmost partition. This is the center left partition. And the idea is we would return to VLM that we found leftmost partition far left red bush. And this would be like this like quick verification loop with VLM. That's exactly where we want to go to. So the thing is, because we are capable of having this like bounding box here, we would have an angle towards this object specifically, and then we besides like despite us not having the hard priors, we would have the coordinates of our drone, and our VLM would also, based because of it has like pretty good spatial priors, and it would be able to provide an estimation for the distance, and we would use the angle because of the bounding box and our position and orientation of the drone, and the coordinates because we still have the GPS and the IMU system. We would be able to estimate the relative coordinates of the far left bush where we want to go to, and then we would just provide these relative coordinates to our level planner, and it would try to navigate towards it. And so the main idea again is that integration of memory. So while we're moving towards it, we would be querying our model to still provide visual descriptions of the environment, specifically oriented for understanding directions, objects, and just describing what is possibly relevant to us. And then we would have these like captions, right? We would also have relative coordinates of different objects, and also timestamps, and possibly just separate objects. But having separate objects is the question of whether we use YOLO-E, that is mostly prompt driven, or YOLO-11, that is OpenSat, if I'm not mistaken. It's still mostly limited to 80 classes, but at least can work prompt-free fully. So we would be collecting this information and storing it in real time with our embeddings model and the vector database as part of the RAG system that we're planning to use. So we consider it scene graphs. We consider it embodied RAG, light RAG, or graph RAG. But the problem is they're still a bit more computationally expensive to be working in real time, or even if some of them are feasible, they provide too much information or reliance on some of these spatial relationships provided by VLM for specifically how they would store information. And sometimes like we would want to rely less on that and have rather like faster speed and retrieve possibly more information. So it would be stored, and then let's say we reach an intermediate object and our VLM is queried whether there is a final target here. If there is not, is there a promising direction? Well, if there is no promising direction, we basically ask, we query our vector database of what's the most like relevant previous position that we can go to and have the promising direction there to explore. And we would then retrieve that information and move to that last promising spot. Yeah, so this is the joint architecture. But then again, the idea is that navigation methods is definitely something that is swappable, and we're going to talk in later slides what are the other options for the navigation methods or navigation like part of the joint structure. And definitely, like our main claim remains with the real-time on-board like deployment and using memory module. So it's a question of whether like even navigation aspect has to be like fully provided. But we can talk about later that and what we consider for future work. Options as navigation is something that's swappable is not the priority for us, is what we want to present. But then again, we have this two-tower architecture, and we can get both the image embeddings and the textual embeddings separately. So there is definitely a possibility of having some sort of attention maps for specific per patch of the RGB image and staying in 2D. Here in the example, I'm not exactly using this idea that has to be tested properly. It's right now the visual is using it's basically generated using a CNN activation patterns across different layers. Specifically, Resonant 50 was used just for the demonstration, but overall it would look something similar. That if we were to choose a white car as our target, we would possibly have like a higher score being represented with the red color as something we would look for. And then another direction is the waypoint generation, but based on the previous projects and even on the example here, where we asked the O3 model to put a red marker on a black car, it did pretty well overall if you think about it. The black car is actually here and the waypoint is here. But then the question is like how to, like, yes, again, we use the stereo camera with taps. So, but how would we project it? Would it be some sort of classical IBDS where we try to perform just like go towards it, or would we use again? Um, would we really rely on the waypoint generation and use this like sort of estimate, because it would be slightly more difficult and less aligned, because in the object detection we know exactly where the angle is for what object, and with distance estimation with VLM we at least place it on some sort of object. There is some sort of understanding of the size, how typically large the car is, and like where it is in the image to understand the possible distance to it, right? But then with waypoints it's a bit more difficult, and other works use a combination of object detection, segmentation, and other parts to try and have the model place a better waypoint. So it would be a bit of a headache and less likely to be explored, but yet to be used, right? Another, I think the most promising direction is taking the inspiration from the reference paper. So because we have depths, we could still project our embeddings and have similarity scores and have all of this embeddings information be projected onto our depths and try to cluster it based on relevancy and try to create semantic race, not specifically for having this like early on in the proximity to our joint, like some voxels for everything, but just for the semantic race and for the navigation aspect of going towards intermediate objects to explore more and eventually find our target and use memory if we end up in sort of that end, right? So this said, our next page will cover the future work and what our intermediate preliminary experimental results are. And at last, we're at our final slide. But before talking specifically about the future work and the setups we plan to go for, I would like to summarize a bit on the idea. Is that again, we want this real-time, online, technically cold start integration of memory module for object search, so as to help us with certain scenarios in large-scale outdoor environments where we definitely need to query our memory and look into past experiences to understand where to go next, instead of aimlessly mapping and exploring areas in between and being stuck with reasoning in certain locations, right? So our early experiments focused on the idea that, well, potentially maybe object detection and LLM reasoning could be good enough, in the sense that we would use these sequential clues that could come up outside of like the environment. So for instance, if we're thinking of a car, right? Like I mentioned this example earlier, that we could be thinking of a parking sign, and then that parking sign means that there's a parking lot nearby and possibly a car, right? So we thought of having to test this and other protocols in 2D environment. So we built from scratch a Pygame based visualization of the whole process. We also wanted to check on fully locally deployed LLM integration, how would it work in real time. So the results were pretty successful, I would say. So we used the Llama 3, 7 billion parameter one, if I'm not mistaken. Yeah, we also had memory integration where we did a simplified variant, not memory reg, but we used the working memory setup where we just put like save in real time, like what kind of objects are visible, are in the vision range. And yeah, so the green block here that you can see, basically the semi-transparent one, is our vision, right? And then we would also have long-term memory. So the idea was that, well, it actually came out as something as a consequence of one of the protocols where we realized that, well, no, not always you have some clues inside, right? So you need to be able to switch back and forth. So that's why we included vision properly, in the sense that our vision would also work as an exploration mapping. So we would be switching between simplified frontier-based exploration and object navigation. And object navigation would be objects that would work as possible clues towards our final target, right? But we used the simplified environment just to test like early on, and we realized that, well, VLM descriptions would be of real help. Like it's almost never the case where objects inside an exploration is good enough. Plus, because of our general direction of going for an estimated onboard feasibility of the setup, we thought that mapping, again, could be memory intensive, depends on the optimization. We wanted to check if we could go without it. So talking now about more of the hardware related tests, mostly focusing on memory and runtime. So those were performed specifically with the already designed and thought of joint architecture that we presented earlier. So we started actually, when it comes to VLMs, for instance, here, we started by looking into different ones like Lava 1.5, 1.6, Quan 2.5, Internet VL3, 8, 9 billion parameter ones with different visual encoders. The problem with those was a bit of a runtime. So the thing is, some of the models have a bit more tuning. If we go for some Hugging Face-based leaderboard, they have like a bit of tuning, like directionally for like chain of thought reasoning sometimes. That sort of improves the performance, of course, on benchmarking, but in reality, when we care mostly about speed and precision, it wasn't good enough for us. So for now, we're yet to properly test it, so that's why we're taking the Apple reported numbers. And well, Apple used M1 Max, which is only twice the memory bandwidth of Orin AGX, the possible device we would be using for onboard. So Orin AGX has only about 200 gigabytes per second, if I'm not mistaken, for the memory bandwidth. But that basically means a simplified estimation. It would run like twice as slow, like basically. The idea is that if we're talking about time to first token, it would be, for instance, 400 milliseconds instead of 200 or so. Of course, for the speed of actual like VLMs, we also care about tokens per second, but those are affected mainly by context size and also the output limits that we set. But in our case, even with fast VLM setup or mobile VLM, worst case scenario, if it's 1 second. And we also actually tested, when we were testing Lava was also outputting, it was all local deployment, was also outputting really good, and like showcasing really good like spatial understanding. It was outputting things in near 1 second, but then again, those were the local tests we did on our own 3080 GPU with like 4 times the memory bandwidth, so not optimal. So fast VLM makes more sense for us. And obviously we're using quantized versions, so, but given the unified memory of 64 gigabytes for Orin GX, overall, as you can see, it's definitely something the whole setup would be fitting. And we would be using a small, I think it would be pricing around 384 feature-long vector, basically, in terms of dimensions, right? We'll be using mixed spread X small model. It's really quick. Same for the retrieval. And this is meant for 10K possible vectors that are being set. And worst case scenario, like even if we were to go, even so, that's not really efficient, like and feasible, I think, battery-wise. But even if we were to go for like hours of exploration, we would definitely not hit. Well, I cannot make this dark lamp, but we would probably not hit more than 10,000 vectors, as in like if each vector is a single snapshot that we're taking in between. But overall setup memory-wise definitely fits us, and this is also assuming the integration of AirStack, which I'm gonna talk in a couple of seconds about. So AirStack is where we simulate things, and in reality, you don't have rendering and simulation memory constraint, but even with AirStack being at 10, 15 gigabytes, it's still okay for that. Just to include it here as a showcase that OrionNGX should be able to fit it. But then also slightly about metrics, and I guess we can transition to how we plan to simulate it. So right now we're still in the setup of integrating everything properly for AirStack, which is AirLab's simulation platform, where they have used the IsaacSim as backbone with Omniverse enabled environments. And then they already have scripts for low-level planner that we would really hope to utilize well, and also collision avoidance. And because we'll be using ZX stereo camera, like collision avoidance with depths is something definitely helps us. And then we're still in the process where we did simplify things like integrating a VLM and not yet performing some large-scale and proper standardized tests to present. But then the question is to be actually testing the full pipeline. And in case navigation, as we said, it was a swappable bar we talked about, would be too complicated for us, we're definitely considering contingency plans, since our main contribution would be the showcase of feasibility of onboard real-time use of memory module for different outdoor setups, so that other larger labs can use it. We could definitely like simplify the navigation by having a large number of possible trajectories that our like paths that our drone could go in. With simulation, I would still have to decide where to go and decide when to use the memory and how, but have it a bit more predefined, so we care less about navigation aspect. And there could be a real possibility of a problem with viewpoints and other aspects that come with this like full real-time integration of 3D. And there's definitely a number of gaps there. For environments, we have certain environments from Unreal Engine 5 already loaded in the AirStack. Some of them are a bit more large scale, so we would say like 1 kilometer radius or so. But it would be ideal if we could use a bit more natural environments with outdoors and larger possibly, so as to cover more of these like possible scenarios meant to showcase where memory is needed, where again we have some crossroads, promising direction, or like two potential targets. Yeah, a bunch of scenarios we'll present later and have to coordinate. But that would be the idea of using Cesium or ArcGIS for integration with AirStack. But then the question is about the surface level quality, if it's enough for the drone and VLM system to pick up on, and if it's like generally presentable and okay environments to work in. Yeah, so we definitely consider like new metrics, because using default ones we'll be using like SPL, SR, OSR, but to showcase the memory usage properly for this kind of cases, it wasn't done before. And like for baselines, we would be using only probably object navigation methods like VLFM, Rayfronts, and Reasoner Explorer. But for metrics, we are thinking of using something like effective progress. So trying to understand like if the in between, let's say like other systems technically have, as I said before, dead end recognition, but honestly, most of the time it's just like to understand if they hit the success or not, and that's it, and stop there. Multi-step is rarely done properly with UAV outdoor setup, with cold start overall. So, but we still would want to showcase that if there's a possibility that
one of the navigation systems is stuck somewhere near a misleading target and is no longer making an effective progress towards the next promising direction that should have been explored, like otherwise if they were to have this memory module. So that would be one of the metrics without going into much detail, like otherwise you can check out the paper and the poster for more information. Then also recovery rate and stall time. But again, these are something that are tentative and still in works. And yes, we hope to get proper results and hopefully present it later, a full showcase of everything working. Yeah, thank you for your time.